Lecture, I would like to explain a very interesting article by three authors. I know one of them, which is Nathan Lineal in Hebrew University, and this article is from 1998. It explains a method to embed your tree into a Euclidean space. So it's very interesting because there are very few articles that have done such thing. Although this problem is quite easy relative to other types of embeddings, but for theoretical purposes and practical purposes, we just review this interesting and important article by this guy. By the way, this guy, I've explained another article from this guy, 1998, Geometry of Graphs, and so you can find it and watch it as well. So we want to so he introduced C2x and D. I mean the least distortion is order of log n. Is less than order of log n, and so the same notation, I mean the same definitions that we use in several papers. Expansion is supremum of f of x minus f of y divided by d of x and y, and we have shrinkage as well, which is the opposite, supremum of d of x and y divided by f of x minus f of y. So when I say that p of x and y, it means that a set of edges on a path that connects vertices x and y. For example, so the first edge could have this weight, the other one could be this weight, and the last one has this weight. So the distance between x and y, I mean by the tree, is just the sum of the weights, and E is in this pi. So in general, f could be a set of edges, and when I say that omega of p of x and y, I mean this thing. So the Bourgain, same as usual, we are inspired from Bourgain's result, which C2 of Tn is theta is order of log n. And the theorem that we want to prove is that if T is a tree and omega be a positive function on its edges, then C2 of T of omega is less than order of log L of T. So I explained two embeddings in this paper. Although there are three approaches, I mean three embeddings. The first one is very simple because you define your embeddings from your tree. As I promised, I want to embed it into a Euclidean space. And so the root of your tree goes to 0 in Rm. And so we map the vertices to some points in Rm. And so let's just define that the first suggestion is that it is the sum of psi of E, where E is in pi of x. And so you need to know what is psi. But psi of u and v, if an edge u and v has these orderings. Psi on u on v is phi of u minus phi of v. And so let's go to the proposition. So the expansion, there is a proposition that says the expansion of the map psi phi is the maximum of norm of phi of e divided by we. So the first choice for definition of psi, is that each element goes to Re. For example, if we have an edge, it goes to the weight of that edge times UE, because you want to map it in Euclidean space. And then phi, just because it sums all of these bases. So this is, for example, psi of E1 plus psi of E2 plus, and you know that this one is by definition U of E1, and this one by definition W of E2, U of E2. For example, U of E1 is this vector. U of E2 is this vector. First null and so you got the idea. And so if we just rewrite this norm, because if we want to see what happens to the distortion, so we need to check the expansion and contraction as usual. So this one is just psi of E by definition, but E is in pi of x minus psi of E. And so if you work on this, it becomes, for example, if we have a root here and then x and then z and then y here, then you can write it as, it becomes just, it becomes the weight of yz squared plus the weight of zx squared. And so the distance between x and y becomes w of e, and phi of x minus phi of y becomes the sum of overall edges in the path from x to y. So shrinkage is the supremum of d of xy divided by f of x minus f of y. And if we just substitute whatever I told you, then it becomes supremum of w of e over w of e squared. So this is maximized when all of the WE are equal. All of them are equal, then it is maximized. So this leads to the upper bound for the shrinkage. And the next thing I want to say is another embeddings. So the second approach for embedding is a bit technical. So before you get confused, so I give you an example. For example, you have the root, it goes to z and t, and it goes to q and x goes to u, x goes to v, for example, n, y, and some other thing, such as s, a, and b. And so we want to define phi of x like this. So phi of x, which is our embedding, is the weight of E2. By the way, this is E1, this is E2, this is E3, this is E4, and so we just label the path like this, P0 of y, because it starts at y. So E3 is just another way of saying P1 of y, and E2 is just another way of P2 of y. So and E1 is just another way of saying P3 of y. Of course, for the x, traversing an x, we have P0 of x, and here is P1 of x. And as you see, P2 of y is just P0 of x, and this is E2, for example. P3 of y is P1 of x, and this is E1. So you got the idea. Now you want to define your embedding, which is E2 plus W E1 U E1. And this is phi of x. Let's write phi of y as well. Starting from y, starting from x. Starting from y, it becomes W of E4, U E4, plus W of E3, U E3, plus the same thing that happens for x. So I mean phi of omega of E2, U E2, and omega of E1, U E1. So if you subtract phi y from phi x, because there are some terms like this that is common in both of them, so this one is simplified to just W of E4, U E4, plus omega of E3, U E3, del 2 norm. And this is just the sum of squared weights. And for example, in general, for this example, it is simple. For general things, you can say that for any path on xy, you get this. And this is greater than 1 over square root of 2 times omega of p of xy. So this becomes the distance. So this is just the distance between x and y divided by square root of delta x and y, where by definition delta x and y is just the cardinality of all of the path between x and y, which, for example, in this example, all of the paths between x and y is just 2. So the distortion of this map is at most maximum of delta and xy. So and maximum, and it takes over is over all pairs of vertices. And because delta x and y is less than delta x plus delta y, so your distortion does not exceed 2 delta of this partition. And so we just need to minimize the distortion, and we seek a partition P, in which delta of P is small. So your partition could be a sum of some partitions of edges of your tree. So for example, if you have an R here, you can do such thing. So the first tree the first tree, T1, is here. The second tree, T2. So you have found a partition. T3 starts from this one. So this is the root of the T3, and this is called P3, and this is called P2, and this is P1. And so you have found a partition. Now, so you do the embedding in each of these partitions in 1, and 2, and 3, and then glue them together. So this is the idea. So this is a modified approach. And the interesting things by doing this is that now delta of your partition is maximum of delta of pi, which is less than maximum of log of 2L. And of course, L is the number of leaves of your tree. So this one is less than maximum of log of 2L Ti minus 2. And of course, this one is less than log of 2L of T minus 2. And we are almost done. And so you see how you can bound the shrinkage. So for example, so you see that this is an important role, that phi of y minus phi of x is omega of p of x and y, u of p over all passes. And so if you calculate phi of y minus phi of x, as I did before, it is just the square root of, or the sum of the weights of the path between x and y squared. And this is greater than 1 over square root of delta x and y times omega of p x and y. And this is just the tree distance of x and y divided by square root of delta x and y. So we just need to find the maximum of this so that becomes the minimum. So the distortion is, so the distortion of the map phi is at most maximum of delta of x and y, where the maximum is over all pairs. And as I said, I'm just repeating that this is less than delta x plus delta y. So the distortion does not exceed 2 times delta of p. So in this article, I showed you how to map from a tree into an Euclidean space. And this mapping, although it is very easy, and I explained 2 methods for such a mapping, it is very interesting and useful in practice because, for example, you map your original space x and d into a tree, as I did in the previous lecture. Of course, in the previous lecture, I mapped it to a distribution of trees, not just one tree. So you use the expectation. And now that you have a tree or a bunch of trees, then you can embed it into Euclidean space. So in this lecture I did this. In the previous lecture, I embedded your metric space, very general metric space, into a tree or a bunch of trees. I mean a distribution over trees. And then so there is a composition. So you have already mapped your metric space into Euclidean space. So you have seen in our, for example, lecture 5, lecture 6, lecture 7, that I did it in another form.